Welcome to MARSAL's demo for PoC21 test scenario number 3. The main purpose of this demo is to showcase the integration of the ICCS optimizer within the CTTC testbed infrastructure. The ICCS optimizer finds the optimal placement for the workloads that are to be executed within the CTTC testbed infrastructure. In this case, we are considering two different types of workloads. On the one hand, we have the YOLO image recognition application, and on the other, we have OLLAMA, which is an LLM type of workload. For the execution of these two workloads, we are considering two different types of nodes, those that are edge-like and those that are cloud-like, whose main characteristic is the delay between the user and said node. The optimizer is also taking into account that the YOLO workload can only be run on a GPU-based node, whereas OLLAMA can operate on both CPU and GPU. In addition to that, we have to take into account that the cost of deployment is higher at edge nodes rather than cloud nodes. With all this information, the ICCS optimizer minimizes the latency and deployment cost based on those requirements. The two applications are being accessed by a UE through a 5G network. Let's now see the different steps of the demo. The first step is to add a GPU to our Kubernetes cluster. What we are doing here is adding GPU access to both MARSAL2 and MARSAL3 nodes, which are representing the edge and cloud nodes respectively. We are now deploying NB-share, which allows us to deploy more than one workload on a single consumer-grade GPU in a Kubernetes cluster. The third step is to deploy the DCGM exporter so that we can monitor different GPU metrics. With this, we will be able to gather information from Prometheus on GPU temperature or GPU power usage, as it can be seen in these plots. We are now ready to deploy our AR application, YOLO, over GPU. Once YOLO is deployed, we can execute it through the 5G network. Here we can see how the GPU temperature and power usage are being monitored while the YOLO application is being executed in a 5G UE. You can see the YOLO application identifying different objects that appear in the screen of the UE. The AI procedure to identify the objects is carried out at the GPU. In a real 5G network, the different applications will have to coexist in the same network. That's the reason why we are now deploying OLLAMA over GPU. OLLAMA needs also a persistent volume to save the model weights. Here we asked OLLAMA to write an essay to prove that it's working properly. The seventh step is to deploy a delay reporter that will provide the information on the delay from our gNode B to the edge and cloud nodes. We have assumed that the delay is a Gaussian random variable with an average of 20 milliseconds for the edge node and an average of 80 milliseconds for the cloud node. But of course, this could be changed to any arbitrary values. The next step is to move the YOLO and OLLAMA workloads using the Kubernetes API. We can define the target node either as cloud or edge. And also we can specify the type of execution target either as CPU or GPU. In the lower part of the screen, we can see how the container is being created and then running. We will now move the YOLO application from the MARSAL2 node to MARSAL3, essentially meaning from the edge to cloud. The final step is the integration, which essentially amounts to deploying a fast API-based infrastructure orchestrator that interacts with Prometheus, creates the JSON workload and infrastructure status files in the background as described in the deliverables and submits them to the optimization engine, then receives the decision and applies the results using a custom-made Python script that interacts with the Kubernetes API and deploys the decisions. The decisions are taken at interval times of 120 seconds, and at each interval it produces the best function placement according to the minimization of the latency and cost.
My name is Miquel Pallaró, and I am with the CTTC team involved in the MARSAL project. In this demo, we have seen the benefits of integrating a decision engine in the mobile network. In particular, we have seen how the decision engine decides the best function placement among the available nodes of two workloads that are running in parallel and that have different requirements in terms of execution device and delays to the user. We have used a 5G network for our demo because we wanted to have an end-to-end demonstration. However, the benefits of this decision engine and its integration can be straightforwardly extrapolated to beyond 5G and 6G networks. Thank you for watching.